Hello, welcome to the special limits. Today I will discuss the special limit number 2, which is 1 plus 1 over x, value power of x when x goes to either plus or minus infinity is also equal to the limit of 1 plus x when x goes to 0, power of 1 over x is equal to this beautiful, magical, super important number e. I guarantee if you have a bank account, you're all using this limit without even knowing it, without even thinking, because this is exactly the simplified model of the compounded interest rate, which is being used in the banking system. X is in general a real number. This limit helps us to resolve those indeterminate forms, mostly 1 to the infinity, 0 to the power of 0, infinity to the power of 0. I came across through the YouTube postings and saw so many clips where you're using software simulations, computer calculations, you exactly look at the sequence and you show that this number exists by using computers. But that is not a proof. To prove it in math, you need to use the previously established axioms, theorems, statements, and facts. You use them logically in a time sequence to derive a new knowledge, new statement, let's say new theorem. And this is what I will do. I will use 4 major theorems: the binomial expansion theorem, the ancient Greece, the Archimedean principle, obviously ancient Greece, the Weierstrass theorem, and the squeeze theorem. First of all, how this number e emerged into our life. That is the 17th century, the Industrial Revolution, when Jacob Bernoulli researched the compounded interest rate. For example, without the loss of generality, when you deposit $1 or 1 monetary unit into account for 1 year term under 100% interest rate, those simple numbers for the simplicity, what will be at the end? Your dollar plus 100%, another dollar, $2. Let's say if this is a compounded interest formula which earns interest on the interest, what will happen if you compound it more often? Let's say every half a year you will get more. At the end of the first half year you'll get $1.50, half of the term, 50 cents plus $1.50. At the end of the second half a year you'll get 50% of that, which is 75 cents. Overall, $1.50 plus 75, which is 2.25. Looks like it's growing now. Instead of $2, now 2.25. So what happens if you compound it even more often? You'll get more and more. Let's say monthly, you will get more. Weekly, you get more. Daily, you get more. Every minute, more. Every second, even more. Can you go as far as you want? And turns out, no. There is a limit. The maximum you can squeeze out of that process, the maximum when you compound it every instance, even less than a second, every instance, which is called instantaneous compounding, and you can jump over that number, which turns out to be 2.72. And this is what you show while using the software simulations, but that is a verification. That is not a proof. In the case of the compounding intervals, we have a natural argument here. Instead of x, I have 1 over n, power of n. N is a positive counting natural number. This is what Jacob researched. And the Weierstrass theorem says, if your sequence is, let's say, monotonic increasing and bounded above, then it has a limit. It is easy to prove it by using the epsilon neighborhood of the supremum of the set. That's the sequence, and those are the 2 conditions. Then it has a limit. So we need to look at the sequence. We need to establish whether it's monotonic and bounded above. To establish monotonicity, I'll look at the 2 consecutive terms while using the binomial expansion, which is known to the ancient Greeks. Later on, it was generalized by Newton. It says that a plus b power natural n is equal to a to the power of n plus m a n minus 1 plus b first power plus n by n minus 1 over 2 factorial a n minus 2 b squared plus n by n minus 1, n minus 2 over 3 factorial a n minus 3 b cubed plus so on, plus, and the last term will be a by n minus 1, n minus 2, reducing up to you exhaust all the n's 2 by 1 over n factorial a power n minus n, which is 0, 1, and will be b power of n. That is the binomial extension. And I will apply it to my sequence, which is xn is equal to 1 plus 1 over n power of n is equal to 1 plus n 1 over n plus n minus 1 over 2 factorial 1 over n squared plus n minus 1 n minus 2 over 3 factorial 1 over n cubed plus so on plus so on. And the last term will be n by n minus 1 n minus 2 so on by 2 by 1 over n factorial 1 over n to the power of n. Let me simplify it now. So x power of n is equal to 1 plus 1 over n. Power of n is equal to 1 plus n over n is another one. So it's 1 plus 1. This is actually 2 plus. I can reduce one n here. So it will be n minus 1 over n, which is 1 minus 1 over n multiplied by 1 over 2 factorial plus. Reduce one n, so it will be n minus 1 over n minus 2 over another n. So it will be 1 minus 1 over n, 1 minus 2 over n, 1 over 3 factorial, plus so on. And the last term will be 1 minus 1 over n, 1 minus 2 over n, so on, 1 minus n minus 1 over n. 1 over n factorial. So n minus 1 terms. 1 n reduces, so n minus 1 up to 1, which is n minus 1 terms here. Yeah? Now, I need to compare xn to x sub n plus 1. So x sub n plus 1 is equal to 1 plus 1 over n plus 1 power n plus 1. And it's equal to, so if you apply the same expansion, it will come out to the same structure, where instead of index n, you will have index n plus 1. So you have 2 plus 1 minus 1 over n plus 1, 1 over 2 factorial, plus 1 minus 1 over n plus 1, 1 minus 2 over n plus 1, 1 over 3 factorial plus so on. It will be 1 minus 1 over n plus 1, 1 minus 2 over n plus 1, 1 plus so on. The last one, 1 minus n plus 1 minus 1. So just n, 1 minus n over n plus 1, 1 over n plus 1 factorial. Here's the second consecutive, next neighbor, next term. And now let's compare corresponding coefficients of the same factorials. 2 factorial, 2 factorial, 3 factorial, 3, and so on. Corresponding coefficients, and you can see that in the index n plus 1, we have 1 over n plus 1. X plus 1 is increasing, 1 over that will decrease. So each time I'm subtracting smaller values from 1 for the next consecutive term, which means that you can clearly see the relationship, all the coefficients of the corresponding factorial terms, the reciprocals of the factorial terms, their coefficients are getting higher because the reciprocals of the larger indices, the coefficients going up. Yeah, this is what happens. That's the trend. And moreover, we have an extra term here. This is the extra term, extra positive term. So overall, from here, here x sub n is exactly less than x sub n plus 1. So it's monotonic and it's actually increasing. Monotonic actually increasing. Monotonic actually increasing. Next, let's establish whether it's bounded. Bounded. Let's establish that. So monotonic and bounded above. So let's look at that. Star. Let's look at the star expansion. So from the star, my x sub n is equal to 1 plus 1 over n power of n, and it's equal to 2 plus all that long summation. And if you look carefully at the coefficients of the factorials, of the reciprocals of the factorials, they're all between 0 and 1. All those values between 0 and 1. It's easy to see that. 0 and 1. You're subtracting 1 over n. n is increasing, so it's a small number, 0 point something. 1 minus 0 point something is 0 point something. So all of those coefficients are 0 point something positive coefficients. So they're all less than 1. So what if I replace them with all the ones? I will get an upper estimate in this case. Eh? So which is exactly less than 2 plus 1 over 2 factorial plus 1 over 3 factorial plus so on 1 over n factorial. That's the upper estimate. And moreover, it's less than 2 plus 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed plus so on plus 1 over 2 to the power of n. We know, starting from the third term, 2 and 2 the same, 1 over 2 factorial, 1 over the same. Starting from the third term, we know all the factorials are higher than the powers of 2, corresponding powers of 2. Then the reciprocals will be lowered. Over the reciprocals of factorials, they will lower, and the reciprocals of the corresponding powers of 2 getting larger, so with higher estimate. So it will be exactly less than the sum. And what is that? That's exactly the sum of the first n terms of the geometric sequence. Yeah, it's the sum of the first n terms of the geometric sequence. And we all remember the formula. It's equal to a1 minus an q, 1 minus q. That's the formula for the sum of the first n terms of the geometric sequence, where a1 is the first term, geometric sequence is 1 over 2. Q is also 1 over 2, it's the common ratio. And an is the last term of the sequence, 1 over 2n. And finally, this sum is equal to, now I can say that my xn is actually more than 2. You can see that. Xn is 2 plus something positive. Those are positive values. So it's more than 2. And it will be less than, exactly upper bound is 2 plus. 2 plus, what is that? Follow the formula, will be 1/2 minus 1 over 2n 1/2 over 1 minus 1/2. So that's 1/2 multiplied by 2. So the 1 minus 1 over, so it's equal to 2 plus 1 minus 1 over 2 to the power of n. That's the upper estimate bound. And when n goes to infinity, actually this term goes to 0, and my upper bound will be actually 3. So from here we can say that xn is less than 3 and more than 2. We just proved that it is bounded above, which means, according to Weierstrass says that the limit 1 plus 1 over n power of n n goes to infinity is equal to, that is the number, which is the limit. It's closer to 3. Euler the Great exactly calculated the first 15 decimal digits of that number, and it's equal to 2.7 followed by the year of birth of Leo Tolstoy, which is 1828, 2 times. 1828, 1828, 4, 5, 9, and so on. That is that magical number E. It's actually number E. It's equal to E, which is approximately equal to that number 2.7. E is the first initial of Euler the Great. It's called the Euler's number, which is an irrational constant. This is not the Euler's constant, because the Euler's constant is another value. This is just the Euler's number, which turns out to be an irrational constant. We just prove the existence of that number for the natural arguments. That's the part of the proof. That's not everything. Now we need to look at the x real. When x real, consider the function. F of x is equal to 1 plus 1 over x, and it's positive. Now x real, my function, when x goes to either plus or minus infinity, will always be positive, which means that x plus 1 over x is positive. That's combined into one fraction. When is my fraction positive? When both numerator and denominator have the same sign, either both are positive or both are negative. The same sign. So this is actually the domain. My domain will be x from minus infinity to minus 1, union 0 to plus infinity. Those are the values of my x. This will be case 2, and this is case 1. So I need to prove those 2 cases for my domain of the real argument. That's case 1, Archimedean principle. I will use a consequence of that. Consequence of the Archimedean principle. There are so many statements of the Archimedean principle. The simplest one says that if you have 2 positive numbers, distinct numbers, a less than b, let's say, then there is such a natural number n that when you multiply n by a plus a plus a plus a n times, you will eventually jump over b. You'll be more than b. For the simplicity, without the loss of generality, I can take, let's say, the small number is 1 and another number is b. And there is such a natural n that you add 1 to itself n times, 1 plus 1 plus 1 n times, and eventually you'll jump over b, which means that any real is more than n and less than n plus 1. Any real number is located between the 2 closest integers from both sides. They're called the floor and the ceiling of that number. It's more than equal to the floor and less than the ceiling of that number. X goes to plus infinity. X goes to plus infinity. That's the case number 1. That's this part, my domain. So then 1 over x, I need to flip the signs. Will be less than or equal to 1 over n and more than 1 over n plus 1. Yes. Flip the signs. So you need to flip it this way. Now add 1 to 1 plus 1 over x. So if I adjust 1 everywhere, nothing changes. It will be 1 plus 1 over n plus 1 is less than 1 plus 1 over x, less than or equal to 1 plus 1 over m. Now let me raise them to the powers of x. Yeah, 1 plus 1 over x power of x will be less than, look at this, 1 plus 1 over m. Now let me raise it. Since the Archimedean principle says x is less than n plus 1, I can use n plus 1 here. Since this is exponential function, the base is more than 1. It's a rising function. and you know that the restriction of x is less than n plus 1, so if instead of x use power n plus 1, for this estimate, this value gets even higher. That's why I will just use less than, no equality. It will be now exactly strictly less than that, and it will be more than, and this gets even less. If I do this 1 plus n plus 1, if I raise it to the power of n, so you can see here, those are the powers. X is less than n plus 1 and more than or equal to n. Now, no equality, exactly more, exactly less here, yeah? And now, when your x goes to 0, when x goes to, not 0, infinity, plus infinity, when x goes to plus infinity, x goes to plus infinity, its floor and ceiling also go to plus infinity. N plus 1 and n both follow it. They both go to plus infinity. So n goes to plus, obviously, infinity. And that is your favorite squeeze theorem. It's a limit case. In the limit case, you can write that, need more space here, so I can rewrite it here that 1 plus 1 over n plus 1 power n plus 1, and I need to divide by one more term, 1 plus 1 over n plus 1, because there was power n here, n plus 1. So by this, multiplied by this term, and it will be less than 1 plus 1 over x, power of x, and less than 1 plus 1 over n, power of n, and multiply it by one more term, 1 plus 1 over n. That's the n plus 1. I can rewrite it this product. And when x goes to infinity, it's your favorite squeeze theorem. Both limits go to, let's say, this goes to 1, and this goes to e. I exactly reduced it to the natural case. Reduced to the natural case. n goes to infinity, n plus 1 also goes to infinity. The same powers, the same reciprocal. This goes to e, this goes to 1, and 1 plus 1, it's exactly this case, goes to e, and this goes to 1. So this goes to 1, and this goes to e. So from both sides, your values go to e in the limit case, which means that the value in the middle, which means that the limit of 1 plus 1 over x, power of x, x goes to plus infinity, is exactly equal to e. I just proved it for the real numbers. When x goes to plus infinity, it's equal to e. Now, case number 2, let me write it down here. Case number 2, when x goes to minus infinity. That's this part of the domain. So in this case, I will introduce a new variable. Let y is equal to minus x. It's conversion. So in this case, y goes to plus infinity. Yeah. When x goes to minus infinity, my y will go to plus infinity. I'm trying to reduce it to the positive case. So in this case, I have a limit 1 minus 1 over y now. However, x is my minus y, but my y goes to plus infinity now, and it's equal to the limit. So combined here will be y minus 1 over y, reciprocal will be positive power, so the y over y minus 1 now will be plus y here power, and y goes to plus infinity, and it's equal to this. I can write y minus 1 plus 1. So it's a limit y minus 1 plus 1 over y minus 1, everything, power of y, y goes to plus infinity, and it's equal to, I can write it as the limit, y goes to plus infinity. What is that? Y plus 1 over y minus 1. 1 plus 1 over my y minus 1. Y goes to plus infinity. What's the power? I can write it y minus 1, and need to multiply by one more term, 1 plus 1 over y minus 1. And now, again, I reduced it to the previous case. You can see when y goes to plus infinity, this drops out. So this goes to 1, and this goes to exactly e. It's reduced to the positive case. When y goes to plus infinity, y minus 1 also goes to plus infinity. The same power, the same reciprocal. That's exactly this construction with a positive trend. So it's also equal to e, and finally, it's equal to also e. And that's the end of the proof. QED. I just proved the existence of this very important number e by using those theorems. Consider the domain, the two cases, positive trend, x goes to plus infinity, my real x, it's equal to e, and x goes to minus infinity by introducing a new transformation, new variable, y, the limit is being reduced to the positive case, and it's also equal to e. I hope that was clear, interesting, informative, and useful. Now you know how to prove the existence of this wonderful number exactly. And I also hope you liked it, enjoyed it. Any questions, comments, please message me. Thank you very much. Talk to you soon. Bye-bye.